This presentation is about how to adapt equations for experimental work. Hooke's law is simple. It explains that if you apply a force to a spring which is clamped at one end, the spring will extend. We can take the equation and rearrange it to make x the subject. Replace our force with the force due to a mass being accelerated due to gravity, and we can basically have a formula that relates mass to extension. So this is an example. We've got a spring here. I've just given it a spring constant of 10 just to make the math simple. So if you were to just use the equation, you would say, okay, for a mass of 0, we should get an extension of 0. For a mass of 1, we should get an extension of 1. Sorry, not 1, 0.981. So on in that fashion you see in the table. When you increase mass, you get an increase in extension. What you get realistically is something like these experimental values here. So for a mass of 0, you don't actually have an extension of 0. There's some extension that happens before you add any mass because of the weight of this holder here. So if I go to the next slide, you should be able to see the holder being labelled. Yeah, so our equation is no longer valid. How do we know that it's no longer valid? Well, if you say m is equal to 0, that should mean that x is equal to 0, but obviously it's not the case. If you just look at it, you can't plug the values in there and make it work. It no longer works. So it's not that the equation is useless, it's just we need to modify it. So we're just try and have a think about how you could modify this equation to make it work for us in this case. So I'm just going to give you like a 5-second pause. So the solution is to change our equation into a differential equation. So instead of just relying on a specific value of extension and a specific value of mass, we're looking at the change in extension due to a change in mass, and they're related to each other through the acceleration due to gravity and the stiffness k. So with this equation, we can pretty simply do like the experiment and figure out k and g if we didn't know what they were, but obviously we do. But we're going to do this from our experimental perspective in a second. So I'm showing you this from the perspective of someone who would have done these experiments but not actually known what the stiffness is. So if you look at this graph, we've got 3 points here and they make this line. This orange line represents what you would get from the experiments, and the blue one is what you would get if the experiments were perfect somehow, but obviously they're not, so you can ignore this blue one for now. So basically what you need is to create a gradient, and you need you can do it with 2 points. If you just have this point and that point, you can see there's a line between them, that would be enough. But it's better the more you have. In this one we've got 3. It doesn't make a difference having an extra one in this one, just because these are perfect values that I got them from a calculator, so they are perfect. But in real life yours wouldn't be perfect, so the more points you have, the better your gradient will be. So you might know the equation y equals mx plus c, and basically what that says is the value on your y-axis is equal to the gradient multiplied by the value on your x-axis plus some constant c. So for our experiment, the extension x is equal to mass times gravity divided by the stiffness k plus the initial extension. So our initial extension is c, and our gradient is g over k. So with that in mind, we can solve for k using 2 methods. The first one is to differentiate, and the second one is to use algebra. I prefer to differentiate, and that's really the better way to do it for most things. In this case, you could use algebra, but differentiation is the way to go for most things. I just want to highlight the difference between ideal results and real results. So our 3 points here, they're ideal because I got them from a calculator. They're just like meant to kind of represent some real results. But in the real world, you will get results like this. These clearly don't create a straight line, but a straight line is what you need if you want to represent an equation like ours. Ours is a linear equation. It needs a linear line like this. You could have equations of a higher order. So instead of just relying on x, maybe it relies on x squared. And in that case, you can tell Excel that you want a line that uses x squared to give a better approximation, and that's perfectly possible. You can go to higher orders and everything, but we're looking at a linear equation, so we need a straight line, and these points don't do that on their own, but Excel can tell you what your gradient is. So yeah, it's best to use Excel. It will take an average of your values basically and create a gradient out of them. So I'm going to show you the level of differentiation you need for the labs. You will be taught differentiation properly in semester 2, but I'm just going to give you the basics. So we're looking for the change in y, or the change on the y-axis, and the change in the x-axis. So change in the y-axis, our smallest value for extension is 0.981 and our largest is 2.943. So do the biggest, subtract the smallest, and you end up with 1.962. Do the same for the x-axis and you end up with 2. If you get the 1.962 and divide that by 2, you end up with the gradient of the line. And that conveniently is, I think it's, 0.981, and that's kind of what the gradient on our Excel graph was before. So basically Excel tells you the gradient anyway, so you don't need to calculate it. But what you might need to be aware of is how to use it to actually realize what the gradient represents. So in our case, we've got x equals m multiplied by g over k. We can change it to be delta x is equal to delta m multiplied by g over k, and then we rearrange it to have delta x over delta m, which is our y-axis over our x-axis, and that's equal to g over k, which is our gradient. So that means g over k is our gradient, and we can rearrange that to make k the subject by doing g divided by the gradient is equal to k, just like we've got here, and that's how you would use that graph to find k. So this is a shortcut that works even if you have an initial extension, because even if there was a constant, like there was in our plot, it gets ignored basically. We're only using the difference in the values. So yeah, think of this as the better way to do your experiments, because algebra isn't the best way. I'm going to show you how to do it using algebra, but it's not like as good. So the algebraic method is an alternative. I wouldn't recommend using it. So if you wanted to do an algebraic method for this, you would have to pick your points carefully, because now that we have this all drawn out and we look at it, we can see these points don't make a line, they're just kind of all over the place. Excel can give you a line of best fit, but realistically only this point here above x-axis equals to 1 and the x-axis equal to 1.75 are actually on this straight line. So that gives you an idea that your points don't really relate to each other very well mathematically. So an algebraic method to like determine k is not the best idea. But if you did like pick one of these values, say the value here for the x-axis is equal to 1, you could say, okay, that's my mass, and then you pick the corresponding extension, which would be maybe 3.5. Just so you know, this is just a graph I found online. This isn't related to our actual data, it's just an example. But yeah, you pick your extension value and your mass value, and you need the initial extension as well. This is another thing. When you do an algebraic method, you need to do some extra measurements, because you need to know certain initial conditions, like your initial extension. The initial extension is like right here where the line intercepts the y-axis. So you need to measure that first for an algebraic method to work. Either way, if you plug all those values in and rearrange to find k, you might get a right answer, but it's not very likely to be right. But as you can see, this value should give you the right one, and so should this one. But even though these points are all over the place, they still approximate to a line that does go through these 2 points precisely. So the main takeaway is, if you have results that are all over the place and don't give you a clear line just by looking at it, if you add a line of best fit, it will go through some of the points, and that should actually give you a very good result. A lot of experiments have been done in the past to find values for like stiffness of like steel and like other metals and stuff, and this is how they found them using experiments. And we have like commonly known values for things now because of experiments like this. And I don't think they used the algebraic method. They might have done, but I'm pretty sure they used differentiation, because it allows you to take an average of multiple results. As you can see here, this line is an average of all these points. So the main takeaway is to use differentiation if you can. If you need help with it in the labs, then feel free to ask one of the demonstrators. But this is just a video on why algebra is not the best way to do things. Hopefully it didn't sound like too biased against algebra. Obviously algebra is useful, but yeah. So this last slide is just to reiterate. You cannot plug values into an equation to solve for something if the equation is not valid. An equation becomes invalid when variables are not defined correctly. In our equation, m means total mass suspended from the spring, not how much mass you have added. But in our plot, we are plotting the mass we have added, not the total mass. So that's where the equation becomes invalid. So one way to keep the equation valid is to include the mass of the holder. And the thing is, in some experiments, it's harder to keep it valid than others. So if you do want to use algebra, you can only use one experiment or result rather than all of the results which you've gathered. It's useful to use all your results, or else you might as well only collect one if you're only going to use one. But yeah, so the algebraic method only lets you use one result, and the better method is to modify the equation for the change of mass rather than total mass. That lets you use all your measurements and contributes to creating a gradient. So yeah, that's basically the end of this presentation.